In Chapter 7, we're going to get into some things that are finally probably not familiar from previous classes. Just about everything else that we've done, you probably dealt with in geometry or Algebra 1. Lines, quadratics, doing different powers of things and different roots. You've done something with those functions and operations along the line somewhere. But in Chapter 7, we're going to talk about exponential equations and logarithmic equations. And those are things, you've maybe heard those phrases before, but I don't think you would have seen any of those in your math classes yet. So now that we're finally in the second chapter of the second semester of Algebra 2, we can maybe say that we're really doing something that we haven't done before. So exponential growth, we're going to look at that the first few sections, and then in section 4 we'll get to logarithms and see what those are. So starting out with exponential growth, you've maybe heard that phrase before, that something is growing exponentially, and somebody might have said that just to mean that something is growing very fast. And exponential growth is a pattern of growth that goes very fast, but there's a little bit more to it. With exponential growth, what happens is as something grows, it gets more ability to grow even faster. Kind of snowballs, okay? Like a snowball rolling down a hill. As it gets bigger and bigger, it can pick up more and more snow, so it's going to start growing faster and faster. So let's look at a couple examples of things that give us a good idea of what exponential growth is. Hopefully you've taken biology and you've studied cell division, so we're going to think about that with one of our first examples here. So imagine starting out with a single bacteria cell in a dish. And let's say that that cell has the ability to replicate itself once every hour. So at time 0, we have just one cell. And 1 hour later, it's replicated itself. So now in our dish we have 2 cells, right? Then in another hour, each of those 2 cells can replicate themselves, so then we have 4 cells in that dish. An hour later, those 4 replicate, and we have 8, then on to 16, 32, 64, 128, right? 4, 5, 6, 7 hours later. You can see that it starts out growing pretty slowly. At first, we only added 1 cell, and then the next hour we only added 2 cells, and then the next we only added 4. But as we went on, the rate at which it started growing was increasing. So as that population got larger and larger, it gives us it gives it a greater ability to grow faster and in larger quantities. So that's an example of exponential growth, where as it gets larger, it's able to grow faster. Another example, think about the last zombie outbreak movie you've seen. It starts with patient 0, right? And let's say that in the first 10 minutes of being patient 0, they go and infect, 4 other people. Okay, that's 14, or that's 5 total people infected now. Well, let's say in the next 10 minutes, each of those 4 goes and infects 4 other people, right? What's that give us? 4 times 4, that's 16 new people being infected. If each of those 16 in the next 10 minutes go and infect 4 other people, that's 64 people being infected in the next 10 minutes. So it grows faster and faster as that population grows. So when it comes to the equation, what it would look like on paper to represent this exponential growth, what we're going to see is y equals a, so that's just our factor in front. That might make it grow a little bit faster, a little bit smaller. But what really changes is we have some base to the x power. And this is what I don't think that we've seen before, is having our variable in the exponent. Okay, so y equals a times b to the x. A simple example of something might be like y equals 2 to the x. and if we wanted to check out some values, maybe we'd start at 0, 1, 2, 3, 4. Plug in 0, 2 to the 0 is 1. Plug in a 1, 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16, right? 32, 64, 128. And so it's an exponential because our variable is in the exponent, and even as that exponent jumps over by 1, right? Even though our exponent, our x is only changing by 1, the rate at which y changes gets faster and faster as x gets larger. Couple other conditions quick for exponential growth is that it has to be positive. So that number, that a in front, has to be positive. If we had y equals negative 2 to the x, that would surely give us a similar pattern, but it wouldn't be growth because this would actually be going down and decreasing. The other condition is that b has to be greater than 1. So if we had something like y equals 1/2 to the x, that would not be growth because as we multiply a half a bunch of times, that's actually going to get smaller. And we'll see that in the next section, actually. That's what we would call exponential decay. But these two conditions, being positive and that base of that exponent being greater than 1, are the conditions that have to be met for it to be considered exponential growth.